This is going to be sort of the combination of physics and chemistry and astronomy. Honestly, this does step away from really what we consider to be the core of chemistry. So, this is fission versus fusion, and these are both two nuclear processes. So, we learned about decays that can happen to a single atom the other day. These are other nuclear processes that can happen. Fission is when you have a large atom splitting into two or more small atoms. So there we see nucleus. No electrons are depicted here because we're just looking at nuclei today. So there is a large nucleus splitting into two new atoms and giving off quite a bit of energy. Fusion is the opposite. You have two or more small, well, just two small or light atoms coming together and forming a new element, again, releasing a tremendous amount of energy. So, fission splitting will happen to large atoms that are radioactive, and fusion will happen to small atoms. It's not this clean. These drawings sort of make it look okay. Well, split into two. There you go. These two came together, and we got a new thing. That's it. It is a little more complicated than that. So this would be sort of a better representation. So, for example, this is uranium 235. This is what is used in nuclear reactors and certain atomic bombs. If you fire a neutron at it with enough speed, this has to happen with quite a bit of force and energy, it will cause it to split. So we get barium 144 and krypton 89. And it also throws out a few more neutrons, which means that if there is another uranium 235 hanging around, it's going to get hit by one of those neutrons and cause another nuclear reaction, giving off three more neutrons. And so it actually takes off. We call that a chain reaction. Fusion, similarly, can be pretty messy. So, deuterium and tritium, these are both hydrogen, but this is hydrogen with a mass of 2 and hydrogen with mass of 3. If these two fuse together, then we get a helium atom now, but it is not quite stable, so it gives off a neutron and makes a stable helium nucleus. It's not easy to get two atoms to come together and fuse because if you think about what's going on with their charges, you've got, again, we're not looking at any electrons here, but the nucleus has neutrons and protons, so it's positively charged. So two nuclei are both positively charged. They don't want to be near each other. They repel each other. So that means you have to put in a tremendous amount of force to get them to fuse together. And so this is not something that you would normally see you've not seen this in everyday life. Both fusion and fission can release energy and do, but not all fusions or all fissions. So fusion happens to lighter elements. So those would be things from hydrogen basically up to iron. So everything on this side of the curve is going to release tremendous amounts of energy when fusion happens. After iron, we get to the fission side. These guys will release energy when they go through fission and split. This is actually what keeps stars the size that they are. Anytime that we see a star, it is being pulled inward by its own gravity because they have a huge amount of mass pulling them inward. So the only thing keeping them from collapsing inward is their own outward pressure from fusion. So stars are giant nuclear reactors, and they're specifically doing fusion. So again, if we come here, this is an example of fusion that happens in the sun. So the sun is a giant nuclear reactor. It is putting together hydrogen atoms that then make heavier hydrogen atoms, combined with other hydrogen atoms, make heavier helium atoms. And so ultimately this chain ends with a helium. But there's a lot of hydrogen in the sun, so it continues to burn that hydrogen. Eventually, as stars get heavier, they start to run out because you'll notice if we sort of pay attention to what's happening here, we're using up hydrogen, but producing quite a bit of helium. And that continues. And so then it starts to make heavier elements. And so we start to get heavier and heavier elements inside a star. And this is actually where all elements come from. Every single element was just hydrogen at the beginning of the universe. We just had hydrogen at the Big Bang. So as a star starts to burn, it burns hydrogen first into helium, and that can go on for, as you can see, millions of years, depending on the size of the star. And then once it runs out of hydrogen, it can start to form take that hydrogen, oops, sorry, can't speak, take that helium and fuse it into carbon. And then it can run out of that, start to fuse that carbon into oxygen. And as you can see, this really starts to pick up the pace. So this will happen for millions of years, hundreds of thousands of years, and then our carbon to oxygen process can be 600 years. Oxygen to silicon can be 6 months. And then, like I said, remember, I just said that iron is sort of this tipping point. You release lots of energy up till that point. Once the core of the star reaches this iron phase, and it can burn all its silicon and fuse it to God, iron by the end of a day. Once its core is iron, now it can't do this anymore. And so all of a sudden, that outward pressure is gone. So, listen, all my little tabs. So that outward pressure pushing the star outward is now gone once that core becomes iron. So once the core becomes iron, in a quarter of a second, the entire star collapses and then blasts outward. And then that sends all of these elements out into the universe. And that is where all the elements in your body came from. It's from a star collapsing. The universe began with only, well, really with nothing, but immediately after the Big Bang, we had only hydrogen. The universe was just hydrogen. This process has happened in stars all around the universe for billions of years. As this star collapses, that does provide enough energy to cause heavier elements than iron. So that's where those come from. But every single element, we've got basically hydrogen, helium, and some lithium that came from the Big Bang. And then everything else is coming essentially from things that are happening with stars. We've got neutron stars colliding, massive stars exploding, cosmic rays. So you can see that heavier and heavier elements are made by these collapses and these collisions between stars. And it all comes back to this idea of fission. So we have different nuclei coming together, making heavier nuclei.